Greetings. In this one, we will be talking about this matrix A, which contains 1, 2, 3, 4, 5, 6 columns. These are each 3 entry vectors, so 6 3 entry vectors, making up these 6 columns. And what I want to talk about here is which of them are redundant, as they are basically linear independent, because what we're talking about here is 6 columns, 3 entries each, and that means that we're expecting them to span R3. Meaning 3 entry vectors, so vectors in 3D space, and to span all of R3 we only need 3 linearly independent R3 vectors. So what I want to do here is look at this matrix and identify the fact that there's actually not 3 as we need, but 6 columns. That means 6 different vectors. But we only need 3 of them to be linearly independent, and then they will span all of R3, and then the remaining 3 of the 6 will be redundant. So the point here is, for me, what I want to do is identify the ones that we can throw away and only keep the 3 important ones. Also, what this basically is a practice of is finding the basis of a column space. So whatever amount of entries each of the column has, we have some matrix. The height, the amount of rows, gives the amount of entries for each of these columns, for each of these column vectors. So we have, in this case, we have a matrix which is 3 by 6, 1. That means that it has 3 rows and 6 columns. That means that each column has 3 entries. And we want to identify a basis for this column space. So a column space, and this is basically the same thing that we're doing. To identify a basis for a column space, we just want to find the lowest amount of linearly independent vectors that spans the column space. And the span of this column space is basically the span of all these columns together. But as I said, because there are 3 in this case, in the case of R4, we will need 4 linearly independent R4 vectors to span all of R4. In case of R3, we need 3 linearly independent R3 vectors to span all of R3. For this column space of 6 vectors, I want to find only, in this case, 3 that will span all of it, because I know R3 will get spanned by only 3 linearly independent R3 ones. So what I want to do is take this matrix and move it into a form where I can identify which columns are redundant. So the technique we're going to be using here is reduction to basically Gaussian elimination and so on. So we're gonna take it to the reduced form. We're gonna use elementary row operations that involves taking a row, multiplying all the entries by one number, all of them by the same one, or exchanging the rows, switching them, or adding a multiple of one row to another, and so on, or subtracting a multiple of one row from another. So these operations we will use to transform this matrix. And we will transform it in a way that we will arrive at an expression where we will have some columns that are pivot columns, and then we'll have some columns that will be non-pivot columns. And non-pivot columns will be columns without a pivot entry, and those will be the ones redundant to us. And only the ones that will still have a pivot entry, those columns will make up the basis for this column space. It means we have 6, just to repeat once again, we have 6 columns, but the column space is spanned by only 3 of them. And so we have to identify the ones that are redundant and only keep the ones that we can that are sufficient. And because the definition of a basis in general, but in this case the basis of this column space that we're looking for, which is the same thing, just saying the same thing in different ways, either looking for the 3 linearly independent vectors among these six ones, or looking for the columns that span, or the linearly independent columns that span this entire column space of this matrix, and so on. That's basically the same kind of idea. I'm looking for the basis for the vectors, in other words, for the vectors, for the columns that span all of R3, regardless that it won't be all of the 6 ones. So we'll now use elementary operations to transform it and look for pivot columns that will be sufficient. So the first step could be, and there's more ways one could start, I would subtract this row from this one. So for each entry in this one, I'll subtract the corresponding entry in the second one. So I can rewrite the first two ones, which won't change this time. 3, 1, 1, 1, 1, 3. Subtract this one from this one. We'll get this. The next thing I can do is also subtract this one 3 times from this one. So that I'll rewrite the ones that won't get changed. The first and third row won't get changed in this step. Minus 5, 1, minus 14, 1 minus 6, minus 5, 1 minus 6, minus 5, 3 minus 9, minus 6. And then the first one also doesn't get changed. And then we can continue. The next step can be, we can add, subtract 5 times this row from the middle one. So I will not change the last one. I will just change the middle one. So this, and the middle one will get changed in the way that I will subtract the last row 5 times from it. So 5 times 0 minus 0 minus 5 times 0, 0. Minus 5 minus 5 times minus 1, 0. Minus 14 minus 5 times, that's minus 19. 12 minus 5 minus 5 times 10, minus 15. 1 minus 5 minus 5 times minus 10. And minus 6 minus 5 times, that's 4. So, just check it once again. Minus 10, this should be minus 15, this should be minus 19, this should be 0. Alright. Then, another thing we can do is switch. At this point, we could switch the second and the third row, for example. So, the next set of steps here. So, in this step, I will switch I just want it to be organized in a way that as we go further down, there will be more zeros from the left side, because that will help us identify the pivot columns. So 1, 2, 5 won't get changed. See, 6 columns. Then I will put the third row in the place of the second one. And then, yes, I will put the middle one at the bottom. Now, we've transformed the matrix already quite a lot. And what would now be useful is to identify which of our columns are redundant. Because at this point we can already do it. There's something called a pivot column. And the pivot column, what it means is, as we see in practice, one can intuitively start identifying it. Actually, in this case, we've already organized the matrix in a way such that we see the non-pivot columns here, the actually redundant ones. So what we see here is that it is a row that from the left side to the left has nothing but zeros here. Nothing, so it's basically also a valid pivot column. So it's basically the column which contains so it is a column that ends the row which has these zeros like this. Or another way to say it is a column where below its entry there are zeros, and to the left of it, to the left of the entry that is still not zero, there is zeros. So this one is a pivot column. This one will also be a pivot column. This one will also be a pivot column. There's also a reason why we organize the rows here, such that we see it. The pivot columns are generally, thereby identified from the left side, because our goal is to be able to identify them quick. Now, as we see here, these three satisfy the pivot requirement. It might be confusing. One might say, oh, so there's actually in general expected to 1 here, but that is even the more reduced form. So yes, one can divide all of the entries in this row, for example, by -1, and then there will be 1. All of the entries in the third row by -19, and then there will be 1 as well. But it's not necessary. We can already identify it now. Also, what we could do is get zeros up here, but that's another piece of work and we don't need it right now. We just want to identify the columns that are linearly independent and also identify the ones that we can take away. So, by this, we identify these three are pivot columns. So always, one can find better ways or quicker ways to find pivots, but in general, the lesson from this experience is that we can find the linearly independent vectors among all the columns, so the linearly independent columns, or in other words, vectors from a matrix, in the way that we reduce it, row echelon, reduce row echelon form, and then we get the pivot columns, and those are linearly independent to each other. Those will span all of it. Those will span what all of these span, and then the ones that don't have a pivot column, that are not a pivot column, that don't have a pivot, those are non-pivot columns, and those can be taken away. Those are redundant as far as the basis. So the basis, if I say that this matrix was called A, then I want to write the basis of A. Let's say I write the basis of A like this. Will be a set of some vectors that span all of it and are linearly independent to each other. And this is the way we identified it. So we know these three are linearly independent. And what is important to keep in mind here is that now here we have the reduced form. So we can use either the columns as they were reduced here, so these three, because we know it's R3 and these are independent, then necessarily these three linearly independent R3 vectors will span R3. So we can either write them in this form, write these three columns as the basis of it, or if we want to go back to the initial form of the matrix and actually refer back to what we had and refer explicitly to it as a matrix which has a column space, and we want the span of the column space, the only ones that are needed to span all these different columns, the only ones that are actually independent, then we can just take the same positions as we found here. So we found here that yes, these left three ones are fine, linearly independent, so we just take these three, and just because in the reduced form, these three positions, the first three columns from the left, ended up being the pivot columns, that means that they were already had the meaning in the initial matrix. So these three can be written as the basis of the column space. So the spanning set of the column space, which is also a basis for it because they are all linearly independent. So I can either write these three or I can write these three that corresponded from the beginning. So I can choose the first three, so 2, 1, 0, and 5, 1, 2. 5, 1, 2. So this is it. So what we achieved here is we found the basis for the column space. Basically, what I write here more concretely is basis for the column space of A, and that is basically quite a straightforward process. So what we had initially was a matrix with 6 columns, but we knew that 3 of them must be redundant as far as forming the basis for the column space of the matrix. We only need 3 vectors in this case. So we reduced it into reduced echelon form. We found the pivot columns, and those are the ones that are sufficient to span the column space of the matrix. So the basis for the column space of A are these 3, which correspond to the column ones that we found here, which are these first 3 here.